time for many details. I just want to indicate a bit what's going on. So let's recall maybe what Domenico had on the board the other day. So when we talk about topological field theories with boundaries and defects and all these things, we axiommatize them by saying there are model functors from a category of n-dimensional boardisms to some symmetrical model n category. Let me write this on the board here. And there's no real need to take notes, but if you take notes, leave some space, because I will, in the course of the talk, complete a big diagram here. So ordinarily we say, okay, take a category of boardisms, and I'll omit some, decorations here, but it's, we thought of as equipped with some defects, maybe some extra structure, but whatever it is, we regard it as a symmetrical model category. And we want to go somewhere to some symmetrical model coefficient category. And symmetrical model category by default is called Z, for the old symbol for partition functions, because it's kind of the local refinement partition functions. And let me just amplify these points just because it's a bit fun. Why do we axiomatize topological field theories this way? It's the axiom of what in physics is called locality, causal locality, that is encoded in the n functoriality of this statement. As Domenico very nicely showed you these pictures on the board, the fact that this is an n functor says precisely that whatever it does on big manifolds is all composed from smaller pieces cut along bounding surfaces of ever higher codimension. And just for entertainment purposes, when you look up causal locality, you find experimental constraints for it. It has been tested up to 10 to the minus 17 centimeters or meters. It was in the 80s, and then I guess with the LHC now it's up down to 10 to the minus 20. So that's sort of where high category theory, as a theory of nature in a sense, has been tested experimentally. That's why we're interested in, just to amplify what is a good axiom. But now, there's the following thing. The theories of physics that we care about is theories of nature, but also most of them that we actually do care about in theory, like the theories we saw maybe in Williams' talk, they actually are not just random such functors. So Lurie's cobordism hypothesis, of course, gives us a super handle on just all of these monoidal functions. We know they're just all given by fully generalized objects in whatever symmetrical monoidal category we can come up with. But if we give you a random such, it will be nothing like what a physicist will recognize even as a field theory. So this notion of field theory is a bit general. So what really happens with the theories that actually do occur in nature, they arise by a process of quantization, where in some form or other you want some geometric data. Maybe I just scrolled over the thing, maybe it comes. Yeah. So you want to start with some geometric data, which you want to call the prequantum field theory, often called maybe the classical field theory, which is a bit of a misnomer. Then you want to apply a process of quantization to it. So this is what I want to talk a bit about. What does it mean to produce such abstract topological field theory from quantization? So roughly it's this kind of story that I'm talking about. But maybe I'll come to this. Maybe I'll make some remarks on how it relates to other formulas. So to start with, to make sense of this, we need to know where is it that physical fields live. So we want to say there's a process that produces such a Z for specifying physical fields, action functions on them, and so on and so forth. So what are examples of physical fields? So this middle board will be the board where the physical fields will appear. So let's put some fields here. So for instance, we saw a sigma model on Williams' talk. I guess actually the target state was called X, right? So in the sigma model you say there's a moduli, if you want to use big words, there's a moduli space of fields, X, which just means in the sense that whenever you have a world volume, the manifold that represents the actual object that is propagating, say, a 1 + 1 dimensional string, then a field is just a map into this manifold. And then maybe the classical field satisfies some properties like homomorphicity or something. But in this sense, X classifies the field, the space of fields, it just maps into X. But not all fields in quantum field theory are classified by manifolds. Often you see in the text books that are sophisticated, they say, in the full theory, a field in a field theory is a section of a field bundle, where by field bundle is meant a vector bundle. And that's actually not true. It's true in perturbation theory, which is what maybe 90% of the time is being discussed. But it's not true in general. If you have a gauge theory, so this would be a sigma model theory here. If you have a gauge theory, and you do it non-perturbatively, then the modular stack of fields is the universal modular stack of G principal connections, which I would always write BG con, so I would just write it moduli. The universal sort of moduli of G principal connections for G are a gauge Lie group. So we've seen these stacks discussed a lot in Uli Bunker's talk, at least the stable version of them maybe. But the important, whatever this thing actually is, the important point is the following property. It classifies G gauge fields in the same way that sort of this manifold classified sigma model fields. A map into it is a G principal connection, but the new aspect is now, if you have two different such maps, you know, if you have two different such maps here, then they are either equal or not. In a gauge theory that gives the whole subject its name, you can have two of these different maps, and there can be a non-trivial homotopy between them as maps to this object here, which specifies, you know, just the gauge transformation and equivalence of G principal connections. In physics, the gauge transformation of these fields. So we need a context. So this phenomenon, you know, it means actually, by the way, I talked about this a bit more last time in Singapore. I won't make this point again, but it means actually the field bundle for gauge theory, for non-perturbative gauge theory, it's a G-gerb, right? It has as fiber BG, not G. Anyway, so this only gets worse as we go to higher gauge theory, like this 2,1 superconformal 6-dimensional field theory, which is supposed to live on the M5 and world volume, appeared in Kevin's talk. And it's famous for supposed to have a non-abelian two-form gauge field. So that 2,0 theory, and maybe I'll come to a little bit at the end, but I guess I won't have time actually, is given by a stack like this. For instance, you can take the string con, stack of string 2 connections. Oh, I should say at this point, so while I talk about the quantization that is in Joost Nuytens, kind of all the motivation, all the input comes from a long series of articles that I have together with Domenico Fiorenza and Hisham Zati, who provided all the M-theoretical motivation for it. And one of the things we discussed in a bunch of articles are these string 2 connections, which is something that appears in some 7-dimensional Simons theory of the field configurations. And there you have connections, you have gauge transformations between them, and then if you have two different gauge transformations, they may have a higher gauge transformation between them. This will be given by local two-form data, whose one gauge transformations are given by one forms, and then you have one up higher gauge transformations given by 0 forms. So we need a context to even start describing non-perturbative prequantum field theory. We need a context that knows about both smooth structure, so we need geometry, and we need homotopy theory. Meaning that kind of thing that knows about the terms of these types have homotopies between them. Elements of these stacks have paths between them. And that combination is known to be, or by definition, you know, if you do that sum correctly, this is what is called infinity topos theory. And I want to talk about it much except for saying that it's just the word for all the kind of constructions that you saw in Uli Bunker's talk. Well, more precisely, here. What did you talk about? Oh, there, yeah. We talk about the stabilizations of these infinity topos. Well, every now and then the actual topos appear, right? When we just took values in just simplicial sets localized. So, what I'm going to do is, in all of the following, and anyone who has ever seen me before knows this, I will assume we had some context H, which is such an infinity topos, and it's really just effectively the one that Uli was talking about. It could be many, you know. There's this axiomatization, what we actually need in order to be able to speak about these things. It just says H needs to have this property of being cohesive, but in actual examples, you should think of this as being, say, in Uli's notation, I guess, take three functors leave some space here, if you take notes at all, from manifolds into simplicial sets, localized, and the whole thing localized at the local homotopy equivalences. Local weak homotopy, the local equivalence. So I wouldn't want to explain it anyway, but I just point to the previous talk. And actually, for physics, as known today, you need actually the super version. You can do the same thing with almost no modifications on supermanifolds, and then also fermions in the picture. We certainly want to be able to talk about fermion fields, but I won't make a big deal out of that. So I have some text here that I just glossed over, I guess. And the important point is now this. So I'm gonna erase the middle board. There's a more important feature which is supposed to stand there. So you just have to keep in mind this. H is our context now of smooth, geometric, higher homotopy types, which everything in the following will happen. You just should know that ordinary manifolds sit in there faithfully, ordinary Lie group ones sit in there, semi-familiar things like this one sit in there, and so forth. Everything is smooth. So,
do you want to look at functors which satisfy the descent?
Yeah, this was the second W. I take the functor category and localize that again at the stalk, well, whatever, at the Czech covers, but it turns out to be equivalent to just localize at the stalkwise homotopy equivalences. So we say if we have two such stacks, which we can test on all manifolds, we have a map between them, which is the natural transformations of the underlying presheaves. We say it's equivalent if just stalkwise. So if for every manifold, and every point in that manifold, and every small enough neighborhood of these points, this transformation restricts to an equivalence of the corresponding infinity group, what Kahn's intuition says there. That turns out to be, yeah. Okay, so this will be the context of the kinematics of the theory. We want to be talking about dynamics and then quantize the dynamics. So how do we encode dynamics in this context? So this picture will, in the course of the talk, refine a bit, but let's start with just something a bit heuristically. So I will write this modular stack of fields, which will be unspecified. It's one of the ones that you just saw here. I'll always write my bold-faced field. So this is to be the modular space of fields. Moduli, infinity stack if you want to be fancy, of fields of our theory to be defined. You can pick just any object in our H and just call it the modular stack of fields, and we're asking what might be a field theory that has, for which maps into this other fields. Right, so one thing maybe to notice here is in this higher geometric picture, the notions of sigma model and gauge theory, they merge. This will actually be important in the very last example, maybe if I do higher WSW models. It's actually important that there's a mixture going on. But anyway, everything is mapped into something as soon as you're in state. So, let's start calling them the incoming fields if you talk about dynamics, because we want to have this picture in mind now that there's some incoming field configurations and then something happens and some other field configurations come out. So we imagine, maybe I'll shift this all up again. This will become a bigger diagram. Let's move it just a tad up. Maybe I'll put it here. Did I anywhere move it? Fields in. Let's call it modular again. And then I just write fields out here.
Are those functors that you can evaluate on any manifold, or are you specifying the dimension of the manifold, or how to evaluate these things?
Well, no, the site I used is the site of all smooth manifolds, finite dimensional paracompact smooth manifolds, or square manifolds. And the maps are all smooth maps. Sometimes people look at this discussion as something completely different. The set of manifolds and état maps, like local differs between them, but that's certainly something very different. So yeah, all men. Okay, so well, what should happen is, if some incoming field propagates to an outgoing field, then it will go through some path, some trajectory, and it will be kind of a field along that whole trajectory too. So we're just going to say the following now. Suppose there are field configurations here. So just another object in our H, which I call field trajectories, with two informations. There's a map here, which I will call I in, which just, gives such a trajectory and tells us what is the incoming field configuration. So it kind of just tells where does it start. There's another map here. It says where does it end. I up. So the example to keep in mind is, all this is super simple. I'm just trying to set the scene. So you get this, for instance, and we'll see that this is of course what our field theory will do. In the end, at the moment I'm just writing down explicit fields, but if you fix one field without subscript, and you fix a cobordism, sigma, a cobordism of manifolds from an incoming manifold, sigma in, which I include as part of the boundary component, and an outgoing manifold, sigma out. This is a co-correspondence, representing this covariance. And just by forming the internal Hom, the mapping stack, we can say fields in is the fields on sigma in, the universal fields on sigma in. And corresponding to the outgoing fields are just the fields on sigma out. And then by functoriality of the internal Hom, we get, and by contravariant functoriality in the first argument, we see that these are fields on the actual covariance. Right, so this is the example to keep in mind. But that's just kind of for trajectories, and what will be crucial in what follows is that once, and this is what Domenico was saying in his talk, once the category of Borgism is not just freely generated just from the point, but from more cells, then it has boundaries and defects, and then you get new such diagrams which do not appear from just Hom-Meg manifolds, which are genuine data. So the other important example, keep it amazing.
Make sure I understand. So this fields in, that's a functor.
Oh,
so I can evaluate on, say, a supermanifold S. And the value is given by evaluating the functor fields on S cross sigma in.
That's right. This is the mapping stack. It works like this. The mapping stack is just the internal Hom in a topos, and it's always given by that formula because it's right adjoint to the Cartesian product. Yeah, so this is what, maybe it's good to say this. What many people in this business, which think that the word stack conjures demons, they will say this is the families version, right? So this is the stack that tells you for each test manifold what are the smoothly U-parameterized families of fields on sigma. But that's just another way of talking about the internal Hom.
Let's say if your stack is something like things with connections, so they have connection data also in the family dimension.
Yeah. So that's an interesting effect. I don't want to talk about this. We have a long discussion, detailed discussion about these different notions of mapping stacks of connections in the article I have with Domenico Ferenza and Chris Rogers, Higher Geometric Prequantum Theory, where we talk about this differential congruification. Yeah. So but allow me not to get into this right now. I just want to amplify the other example, and I have to apologize for doing this by erasing here. The other example of these kinds of correspondences of importance, and this is like in Domenico's talk, is once we put one boundary condition to board a full codimension, there will be, by definition, correspondence of the form where we say there's nothing here. So you take the incoming fields to be just the field on the empty thing. There's some bulk fields. Whoops. Field bulk, and some boundary fields. This will be a boundary condition in the prequantum field theory. We'll see, trivial as this has kind of remarkable. Maybe I won't make it into this. I have these very detailed notes that I'm showing here, which you can find if you just follow the links either from the conference abstract or from your thesis, and maybe you can, if you're interested, look it up. Yeah, here I have this example. I just show this maybe on the screen, just to connect to other talks we had. If you, of course, take this is a general statement about functorial field theory as opposed to algebraic quantum field theory. If you look at the special covarianisms that have kind of a bunch of this coming in and one this going out, and think of it as being a morphism here with boundaries, kind of for open branes that merge. And then let me draw this here. There are covarianisms of the form. An open brane, another open brane, another open brane, moving around, interacting, and fusing in the simplest genus 0 case to one new brane. If you're kind of one-dimensional and two-dimensional guy, you look at this from here, and then you just see one disk with lots of disks in them, and you see some product operation that merges, whatever the field theory assigns here to the big brane. So this is a bit how it connects to the factorization algebra, but I won't get into this at all. It's just to indicate that I'm not talking about something completely different. So here's a little fact which you can check, or it's simple based on something more subtle, but anyway. So every object, I haven't even said it. So we will axiomatize this thing. So we want to talk about these correspondences, and so I will call this, I will introduce a category. Symmetrical not an n category, but let's think of it just as an ordinary category. Correspondences, n-fold, and the n-fold. Let's just ignore this for a moment. In H, it's just a category whose morphisms of this form. The objects are those in H. A morphism is such a correspondence, and composition of morphisms is by taking fiber products. And since we're in topos, everything exists. So you don't have to worry, even if things are manifolds and the fiber product might not be the manifold, you might not have transversal pullbacks, it doesn't matter, it's all. You can go to the derived topos even, and then, anyway, so you have to worry about nothing here. You have this killer of correspondences, and a little effect is, yeah, no, what I've drawn doesn't. In the full, I will show it in the examples. In the full story, we'll talk about an n-dimensional field theory. It will along kind of one-dimensional trajectories look like this, but then this whole thing might move. So there might be fields here that have trajectories to there. And here might be fields, and here might be fields. You draw. Maybe I did have a diagram. You see, we will be talking about n-fold correspondences. Because with an n-dimensional quantum field theory, this might be stuff assigned to a point. This will be the trajectories along a line. And we will have field configurations that tell us how to move over surfaces and so forth. It will be n-fold correspondences. I'll have some picture later, so let me not try to scroll around because I'll just mess myself up. So a little fact is, a little proposition or fact, I don't know, this is kind of fact. Every object here, object in this spans, in this correspondence category, is automatically self, can you even read this? I'm saying self-fully dual, fully dualizable. So it's fully dualizable in the, this statement just means it's a dual object in the sense of monoidal category theory, but it's even a dual object in the sense of n-fold monoidal category theory. It has full dual structure, and it's its own dual in correspondences. And with a symmetric, maybe I should say this, with a symmetric monoidal structure induced from just a pointwise Cartesian product in H. And then there's the following simple but pleasant and actually important fact. It means that the covariance hypothesis proof of Lurie tells us that symmetric or just monoidal n factors here are just fixed by their values on the point. So they just fix one modular stack of fields. And then you work out another little fact that this works as such. I think Domenico briefly mentioned it maybe for the case of discrete, where everything worked not in smooth infinity group words, but in geometrically discrete infinity group words, that this functor defined as well will take sigma to the following. It will again produce a mapping stack of fields, but it will produce the classical fields, the flat fields. Namely, it will form the mapping stack out of the discrete homotopy type. Yeah, and now so this for me is pi sigma, because it's the fundamental infinity group word. So this is sigma, or I guess what Uli was writing as curly H. Is this right? What is sigma? And it's the mapping stack, so it gives you kind of the flat fields, the local systems of fields on sigma, but in smooth families. Well, anyway, this is what it does, and then you can work through this. So this assigns phase spaces, if you wish. I mean, it's a bit slight abuse of notation of terminology. If our theory is a high chance theory, then maybe, or maybe not come to this, then it's exactly the phase space, because the classical fields are precisely flat.
So the monoidal structure of correspondence is just induced from that of spaces.
Yeah, you just do it. If you cross two such things, it's just, yeah. And an important fact is, you use the Cartesian product of H to define it here, but it's far from Cartesian as a product in correspondences. Correspondences, they're beginning to look quantum already. They have quite a, funny, or, a non-Cartesian monoidal structure. In particular, since, products and co-products coincide, since the category is just equivalent, evidently, to its reverse. So, okay. Yeah, I guess I won't make it very far, but I will probably be able to tell you the story. We just need to find an eraser, and then we can actually continue. I lost it.
Oh, yes.
I know, thanks. So this is still not, so we're beginning to pass from kinematics to dynamics. We know how things move, but actually for doing physics, in quantum theory, we want to assign our probability amplitudes, squares of probabilities, to all such trajectories. That's really the point of quantum mechanics. And then you want to say, you do some kind of funny statistics to find out what the actual propagations are. I'll formalize all this, or I'm claiming it can all be formalized like this. But before we get to the full picture, to motivate a bit, let's see how we would formalize this. So in the standard, if you think of the case where this is maybe just field conversions, just a particle propagating somewhere over a curve, then you just want to say to each point in here, you just want to map, you want to assign an element in U1. So this is called the exponentiated action functional. Even though, so I might talk just to stick with physics notation, we'll always look at xis, but I, in general, will not be exponentiating anything. Of course, in the special examples often I will. The whole point is that actually this exponentiation is itself a kind of subtle thing. You really need to be exponentiating higher gerbs. Anyway, so it's just notation for this map. It will always be x by s. And we want to go to U1. Now this is not a very, this is a stupid diagram of this sort. This doesn't, you can write it down, but it doesn't help you at all. So let's use the following fact of homotopy theory. Since we're looking at transformations that should be valid in U1. So there's this universal construction, which is of course the looping construction. If I take BU1 here, the smooth version of U1, the stackification of the chain complex of U1 valued functions move to degree 1. And let's suppose the incoming field is actually trivial or something, and nothing is happening here. Let's take this to be the trivial functor for the second. I'll change it in a moment. Let's this take to be the trivial functor. Then, by the homotopy fiber product property, U1 is precisely the loop space internal to H, the smooth loop space of BU1. So we get these. So I'm take these for a moment to be points here. And this is the homotopy fiber product over this, and by the universal property of the homotopy fiber product, we get this map induced here. So we can talk about an action functional. I should say you get this map induced by just having any natural transformation filling this diagram. Right? This is what the homotopy property says. We have some cone over the point inclusion is the BU1, then it maps into the homotopy fiber. So what we're going to do to emulate this is we're just going to say, just consider, this correspondence over BU1 filled with a homotopy. That's the same thing as putting an action function on fields. And now if you think about, maybe I'll show this on the slides, think about what happens, for instance, in an ordinary case where you quantize a particle propagating on, yes, sir?
Can I ask you a question about that last statement? So you say it's the same thing as a natural transformation like that. I mean, putting an action function is describing an actual function. I think what you're really saying is that in some sense that's homotopy equivalent.
You see, we're in the top, everything is smooth. So if this happens to be the stack that is represented by a manifold,
yes,
and then this is U1 as a manifold, then this map will be automatically a smooth function. It's not just a map of homotopy types, it's a smooth function.
You're trying to classify those things by these maps of the transformations in this diagram somehow?
Yeah, smooth functions from here into U1. Since U1 is this is a little lemma, maybe I should have amplified this one. Can check easily, maybe it was also in Uli's talk that the smooth group U1 is the looping internal to H, not internal to spaces, of the stack BU1 is a smooth stack.
Yeah.
And then I'm just using here the universal property of homotopy pullbacks, right? If you have a diagram ACB, then if you have any cone over it, homotopy cone, it universally factors through all up to unique homotopy through this homotopy fiber product. And we're just using it for the case that this is BU1 and this is U1. It's a smooth thing. Right? So look at, I don't want to draw it. For those who know, if you point as a particle which is charged on some propagating as a manifold X, charged on some gauge field, then the action functional over an open path is actually not a U1 valued function. It's a section of the pullback of that bundle to the endpoints of the string. Right? You have to kind of trivialize the quarks at the end of this particle to actually get a number in U1. What this means, if you go through it, that I is the interval on the top of the path, the smooth path space of X, chi nabla is stupid notation for the underlying U1 bundle of our electromagnetic field. It just means the actual action functional over an open interval of the charged particle is a homotopy like this, where the point is that here and here we do not have the trivial U1 bundle, we do have the background gauge field. So what we will do now, following this article that Domenico and Chris on higher Germanic prequantum theory, we say, well, the background gauge field is not a map to U1, it's a map to BU1, And since we want to think of extended quantum field theory where the stuff, in low codimension is supposed to be obtained by transgression from the stuff in high codimension, we can just call this thing here now a higher action function. So we'll call this now a local action function. And maybe if you want, we can go to this differential refinement, which I always put I always write this subscript con. Udi thought it was maybe with a hat. So we will look at the following situation. We have incoming action functions, outgoing action functions. And then some trajectories. So again, we can ask, well, okay, so I can just draw any such diagram, of course. But let's turn it into a prequantum field theory. And then first observe, so we want to kind of refine the correspondence in H. And look at the full diagram that I've drawn here. Is now actually a single correspondence in what is called the slice topos. You see, it's just that everything now lives over a new coefficient object, which is this maybe differential refinement of BU1. So this whole thing lives in correspondences in what's called the slice topos. So the slice topos is something whose objects are maps into BU1, and whose morphisms are precisely such homotopy commuting diagrams. And higher up, keep displacing here. So there's a category, symmetric monoidal infinity n category, n-fold correspondences in the usual notation like this. You slice over our coefficient object, and of course in the full theory now, I will take this to be the n-fold Debye thing. Right down on the points, we want to have these n bundles, so that when you transgress all the way up, you find ordinary probability amplitudes of the ordinary trajectories. Maybe I should say a thing about examples at this point, but I kind of postponed them to the end. So if you're wondering about any examples here, like I have a huge number of articles with, or a large number of articles, Domenico and Hisham, or lots of examples of things that are classified by these. In general, these are like transitions. Yeah, let me give you one example, e.g. 3D transitions. For 3D transitions theory, fields would be BG con, as we already saw the map at the moduli stack of gauge fields, and then it turns out there's a smooth and differential, or maybe just differential now in the new terminology, refinement of the, if this is a simply connected Lie group, it has this canonical kind of Chern class, and what we constructed was this smooth refinement of, or differential refinement of this, which goes to B31 con. So it's something that locally assigns connection 3 forms and globally knows about the topology involved. You should think of this as being the Lagrangian, maybe, of Chern-Simons theory. That 3 form is locally the Chern-Simons 3 form of a given G connection. In the field theory, the action function will be given by transgressing it to codimension 0, which just means we integrate it.
So in this case, this field in, field out, and field trajectory is all the same, yeah?
They will all be given by, if this is an actual trajectory, by diagrams like this. So, I can just draw any such diagram, that's one story, and then I can start asking, do these diagrams form a field theory, in the sense that they arise as images of cobordisms.
Should we give a correspondence in fields? What is correspondence?
Yeah, so we had so far discussed correspondences in H. That was just the field content. We were just assigning modular space of fields to manifolds. And now I'm saying, let's look at correspondences in BNU1. Con say.
But is this example?
This is not a correspondence yet. It's something just in that.
It's an object.
No, in the slice. You see, this is now one object in the slice.
Yes, what is the correspondence?
This is another object. This is a morphism in the slice topos. And this is another morphism in the slice topos. So the whole thing is again a correspondence in the slice. Morphisms in the slice are just commuting triangles.
So what is your example? Then you should give a full correspondence. You take all the identity elements, yeah? Everything the same. And
Take all what?
in order to get a field theory, you have to give a correspondence.
So this is just one morphism in here.
Yes.
Okay? So now we can ask, so what is it to have a field theory? Sorry, maybe I skipped ahead. So now I can ask, what does it mean to have a symmetric monoidal functor here? And another little fact is, every object here is fully dualizable, and every object here is fully dualizable, has full dual given by x minus is. You take the same field conversions and you change you take the negative with respect to the abelian group structure of this group stack. There's a little thing you can check, and so all the things will be dualizable. So the upshot is having this lift here of the field conversions is precisely the same data. Maybe I should put it here. Precisely the same data as fixing one moduli stack of fields and fixing one extended action function.
And you're just working with frame for
You know, as I said, yeah, that's right. For this statement to be true, it's framed.
So you're describing the dualizability properties in the category of correspondence.
Yes. And that's a little computation or a little observation or one has to make. It's, you know, why I'm saying observation, all this, I mean, these kinds of statements are kind of all throwaway remarks in Nuri's TFT article, and then one can maybe feel inspired to try to check them, and then when you check them, you don't know, did I just do something, or did I just check what Nuri did?
So may I ask, I mean, maybe I didn't, so this diagram there would be an object in core 1?
So this is an object in core 1, or in any core n.
Oh.
And this is one morphism in core n, or one morphism. And then, you know, the higher correspondences become hard to draw, like correspondences of correspondences. So you start taking another field conversion here, mapping there and there. And everything with ever higher homotopy is over BNU1. So I should say, so this picture, so I have something almost like this in some unpublished notes, it's on my webpage. But to be frank, this for H, just discrete infinity groupoids, geometrically discrete sort of infinity groupoids. This is the perspective in this little conference proceedings. Fried, Hopkins, Lurie, Taylor, section 3. Then they discuss this for H being discrete infinity groupoids, which is the case. You know, all these fields are discrete infinity groupoids. So maps into it are gauge fields which are just flat. These are what's called Dijkgraaf-Witten, higher Dijkgraaf-Witten theories. So what Fried, Hopkins, and Taylor in this article sketch, it's very, I don't know, it's just a conference proceedings maybe. They sketch how one might quantize infinity Dijkgraaf-Witten theories, high analogs of Dijkgraaf-Witten theories like this. And if you wish, what I'm trying to talk about now is how do you refine this to actual field theories that appear in nature? I mean, Chern-Simons is already a bit of a toy example, and Dijkgraaf-Witten all the more so. Right? The thing is, the actual theories in physics don't have discrete moduli stacks, geometric discrete ones. The easy, or what makes things relatively easy for the discrete case, is that you have kind of the high analog of the counting measure. So once you want to integrate, you just sum in the right way, which is still subtle enough. So there's some Lux Enco limit involved, but in generally it's just some canonical construction that just is there. You just have to make sure that things are kind of dualizable enough. What I will be concerned with is now, how would we quantize such correspondences if we have actual geometric data? Yeah, I guess I will just barely make it to that point, but let me just keep going this way. So I have a bunch of remarks on examples. Here's this, what I just said. Here's the lift. Here's the boundary condition. So now we want to quantize. And now, yeah, my plan was actually to gradually refine this diagram, but I now completely messed it up, so I need to clean a bit. Not bad. So the main diagram will stay. And now we do this. So think about what quantization is in ordinary quantum mechanics. We have some coefficients in U1, and we understood, you know, some probability amplitudes. Yeah, let's maybe write this probability amplitudes. Action. And now to quantize, what one really uses is that you want to add these things up in a way that they interfere. So one needs a kind of, this is the superposition principle of quantum mechanics. This is really the hallmark of where it all comes from. That you say all these values are kind of supposed to be two things. You have to be able to add them, and not just in some free additive group. They have to have the possibility of to additively cancel. Right? So in ordinary QM, you use the embedding U1 sits in the group of units of the complex numbers, and that whole thing, of course, easily deloops smoothly to map from the model stack, just the looping U1 into, so these are kind of circle principal bundles, these are GM line bundles, and in any case, this is the same as C lines, complex line bundles, and they sit in the category of all C modules, which of course is just vector spaces, the stack of vector spaces of C. So in a way, this is the linearization step that's involved in ordinary quantum mechanics. So what we're supposed to do is we need to have the analog of this step, and since we're now in homotopy theory, we just make the same statement. We have a map from a group of phases, as it were, to the group of units of a ring. So ring now will have to mean E infinity ring, or ring spectrum, and it has a group of units. It almost maybe appeared in Urs talk, so maybe I can just write let be any1 here, so there's an n. So we're going to fix a map rho, which I will call the choice of, it's maybe the choice of superposition principle. If you wait like just to, maybe it's fun to, formalism kind of follows what's supposed to do. Anyway, so we can form, suppose we have a ring spectrum. So in practice, I currently only know how to do this externally, so for geometrically discrete ring spectra. In principle, you can do it internally. I think we're just going to be working on this. But so anyway, what you can do is you take an infinity ring. Let me just write E is an community of infinity rings, and there's an infinity group, a connective spectrum, an abelian infinity group associated, which generalizes the usual group of units, and we can ask for such a map. And this is, by analogy at least, the right thing to do. Now we should maybe check that it's also in practice the right thing to do. And so the beautiful thing about this, which of course was nicely explained in a series of articles by Ando, Bloomberg, Gepner, and I suppose also in related but other objects is also Resch and Hopkins, if I remember correctly. So they have articles where they kind of say, they think about what is twisted generalized homology theory formulated nicely in a homotopy theoretic context, in an infinity category context. And it comes down to the following thing. BGL1E identifies, just as it did in the simple case there, with the E lines. Oops. So this infinity group what these objects are E module spectra that are equivalent to E as E module spectra. And those morphisms are E linear maps. And that sits in E mod. And I guess E mod was on board in Urs talk that HC mod was on board. So there is, I'm not gonna, but the nice thing about high category theory is you don't have to, so it all works just as you expect. It's the category, those objects are, infinity abelian groups equipped with an E action and so forth. Only that now everything is an infinity in front of it.
What is in this discussion?
Oh yeah, right, N, sorry, thanks for saying. So it's this N. I want to talk about n-dimensional quantum field theories, and by this little motivation I didn't make this clear. I want them to be such that in codimension 0, the prequantum theory assigns elements in U1 in the slice sets. So that's why the loop n times. I should, this is a long story. Last time I gave some lectures just about kind of this part of the story and how you see the examples. So think of transgression, right? You have n forms down in codimension n, and then by transgressing you get n minus k forms. So we have this linearization step, and you can maybe first, it's best to think of it as really just being a representation of this group, an E-linear representation. But putting our B's in front of it and using the fact that everything is stacks, this is also the thing. This is the universal map, from the universal n stack of circle n bundles to the stack of E modules. So this is the thing that takes a circle principal bundle to its associated E module bundle which is associated via rho. So this composite here, this I will call L in. This is so in codimension 1, if you have a B1 here, it turns out that these maps play the role of the prequantum line bundles in geometric quantization. So in this homotopy theory, which lots of notions that are ordinarily different converge. The local action function is at the same time it's Lagrangian, and it's at the same time it's higher prequantum line bundle. So for these things, maybe check our article Higher Geometric Prequantum Theory. I want, I guess I'm almost almost done anyway, three-quantum theory, for kind of everything up to here, with Domenico and Chris Rogers. So you have to just accept this. This map will be, so if this is the prequantum circle bundle, this is the principal one, this is the prequantum E-line one. And in, you have one out and out. And the whole thing now, if you analyze what this is really a matrix of E-linear maps between these fibers. This is what now that we E-linearized, what do I do this? Maybe color, if I had color. The whole thing, let me do it in both. The whole thing is what you would call, over E, it's the integral kernel. Okay, this is a bit of a mess. Imagine it's red or green. So this is the thing that you want to put into the path integral. It tells you for each trajectory what is the E-linear map that is assigned to this trajectory. And the path integral is supposed to integrate these E-linear maps for fixed fibers of all trajectories. So what we need to do, and this is not the crucial step, we need to do the path integral. And you see, if this is the prequantum line bundle, then the quantum states, the wave functions are supposed to be its sections. So, well, and there's a little subtlety here, which is super deep maybe. Of course, actually the wave functions in ordinary geometric quantization are polarized sections. We will not polarize it. Polarization will appear automatically in higher codimensions. So we just call them wave functions of quantum states. But this is, if you're wondering what I'm saying here, go to Jost's thesis. I think it's beautifully written. He explains all this kind of from the beginning to the end. So what is it? It's just the sections of this. We want to form sections of L in. And this is maybe in part, it's folklore, but it's made super nicely elegant in this article here by Bloomberg-Geppner. This space of sections, maybe assuming that it's fiber-wise dualizable, but this space of sections is the L-twisted E homology of fields. So, if fields is an ordinary homotopy type, so you see what I mean? It's the generalized E homology of this space twisted by this E module, which just means an ordinary E cohomology, you take an E cohomology cluster to be just a map to E. Now in twisted E cohomology you have, I guess it goes back to Rosenberg or something, in K-theory, you have instead of just a map to this typical fiber E, you have a section of an E bundle. And this shows just what's happening. So this is E homology, and I will actually dualize, if we just take dual sections, it doesn't matter much if everything will be dualized, but anyway, so sections and dual sections will. So I'll take this to be the L-in twisted E cohomology. And then here we have.
So can you explain what so fields is an object in your topos, I guess? So I'm a little bit lost with this.
Yeah, so you should think of it. So you see, in the examples that we'll actually talk about, E will be a discrete, what was the notation, the delta or constant. It will actually be obtained from an infinity spectrum in infinity group holds, transcribed here. And then by the adjunction, by the cohesion adjunction, which is in Uli's language is the H.
So this is the diagram in H.
So it will just be what you ordinarily think of the geometric realization of pi field. So we have this functor, H sits over infinity group holds by geometric realization functor, which I call pi, which Uli's talk was H. And by adjunction, if E is discrete, as it is in the example that I will not show, then this is just the ordinary E cohomology of that homotopy type. And if E is not, it's kind of clear from what I will not say, that all this will have an internal version, which I think at least for K-theory really has some good ideas about. And then you will take internal sections and get internal thing. But I know abstractly that this exists, but I can't tell you much about it. So for the moment, we'll be working with.
Yep.
So in the first example, which I won't show, E will be Ku as the ordinary Ku spectrum, just discretely. That was this const K. No, this is.
Yeah, but that's a diagram in H in your topos.
It's still a diagram in H because this reflects.
Yeah. Yeah, okay, so okay, I see.
So everything is in there. I mean, I call this the axiom of cohesion because Levier proposed this. This is what makes the whole thing tick. Yeah. So you see, so we're almost not done. So by this construction of choosing the E, choosing the superposition principle, I should keep that word because it's kind of fun. We can linearize correspondences in the slice of our circle N connections to co-correspondences in E modules, right? So I quantize this, pre-quantize this to the L in-twisted E cohomology of the Laurent stack of incoming fields. And now I'm running out of trouble here. And on the right we have the L out-twisted E cohomology of the Laurent stack of the outgoing fields. And since this functor with the cohomology here is contravariant, we get a cross-span. Here will be the, equivalently, the cohomology twisted by, say, I out star of L out, the pullback of that bundle. And here it will be of the Laurent stack of field trajectories. And the method will go like this. This will be I in star, pullback cohomology, and this will be I out star. Okay? That's just linearization. So we want to start saying that C is something like E modules. Right? So these quantum states, the space of quantum states are themselves E modules. These are the E modules, the cohomology module spectra. So we want to say it's some n-dimensional version of E modules. You can take just the n cubes, maybe in E mod. Depends a bit on what exactly you take the n-fold correspondences to. So in some way or other, we want to go from here to here. So this won't exist on the nose, but this would be the quantization step. Now to actually quantize, it's now obvious what we should do. We have a wrong way map here. We would like to have a direct map here, which is the actual path integral. So we want to turn this map around, and we turn it around by twisted Umkehr maps in twisted cohomology, as I guess explained in this article. But I think, my biased opinion, that if you go to Jost's thesis, that he explains it in a bit more transparent way, but it comes from these four people, I guess. There's a general mechanism, and it also appears, I should say, this is the same mechanism that we saw in Cohen's talk at the first day, where it was applied for E, the sphere spectrum, for doing string topology. So string topology in a way is an example of what I'm talking about, where we take E to be the sphere spectrum, the integers sort of, the want to be integers. And you pull, you have no twists, at least in this, so far in the literature, and you're pushing along maps of, mapping, loop spaces. So, so I have some details here on how the pull-push works, but I guess I'm out of time anyway, or I don't know how much time I have. But, 5 minutes. Oh, thanks. But the thing is, once we choose an orient, so what you're supposed to do is, you choose some category, maybe a very small subcategory, depending on what you're able to do. So this results in the literature. One can do it for some small categories here, but in general, of course, you can ask the question. Oh, whoops. Over B GL 1E. So what you should do is you need to equip these correspondences with orientations. These orientations will be, these play the role of the path integral measure, because you work out at the examples, or you just analyze what it means to do integration of differential forms in this language of ordinary cohomology. The choice of orientation is a Poincaré entity that chooses you how to push, it tells you how to push. So this choice will really tell us what does it mean to integrate this map and go in the wrong direction. you can, for instance, take this coord or to be just a single correspondence sitting in here with a single orientation chosen. That actually happens if you're quantizing a boundary condition, because then there's no functionality condition. Anyway, so what we really need is, we need a lift here. We need to equip, we have an extra functional on fields. We need to equip it with a path integral measure. So this goes by, the standard terminology for this is x by s d mu for some path integral measure. And then you can hope that once you have this, well then if you have this by construction, you take this map here, which is just 500, given by 5 integration differential cohomology. And so making this a functor is a subtle issue. There's an article by 3 Hopkins called Consistent Orientations of Moduli Spaces, where they claim to have solved this for E being KU and this being a subcategory of correspondences of local quotient differentiable stacks. And that's already subtle. So what Joost actually did in his thesis is he didn't actually consider the functionality of this. We just take single such correspondences, in particular those that encode boundary data where there's no functionality to impose, and just quantize them. And by unique, anyway, so he hasn't solved the problem of quantization completely yet. I think it's the right step. So you see, once we have this, then we can say, aha, now we've realized our original Z, the one we started out with, is arising from via quantization from geometric data. And then by just putting this together, you see it's the composite of the functor that integrates fields, which is this data, over this space and integrates the action functional. I mean, I'm just putting, composing these functors. X by s d mu phi d mu phi. That's the, I'm just making, of course, just playing with the notation, but that's the usual notation for the path integral. And the proposal here is, this is the right way, or maybe a right way, to axiommatize it. And so that's a proposal, that's an idea, and then you want to know that if it works. And maybe in the last 30 seconds, I have a list of examples here. I close just with one thing. There's a bunch of examples here. There's something on this 5-frame theory, but I won't get into this. What I want just to amplify is this bit, and then I'm done. So whatever this is, it should reproduce ordinary geometric quantization and just ordinary quantum mechanics. This is the first thing you want to check, otherwise people will laugh at you. And so here's the interesting way that if you find in your thesis explanation how it works. So suppose you have a Poisson manifold, x pi, and you want to quantize this Poisson manifold. Then, I discussed a bit in the examples, there might be a naive idea you have that it doesn't work, and then you say, oh, is the whole thing broken? And then you realize it doesn't work, but for a good reason. So you can make the following observation. There's something called, which I call the non-perturbative Poisson sigma model. So there's something called the Poisson sigma model, is you take the Poisson manifold x pi, it induces a Lie algebra called the Poisson-Lie algebra, and there's a famous construction of a perturbative quantum field theory called the Poisson sigma model, which considers fields on this Lie algebroid. It's a famous result of Cattaneo and Felder that the perturbative BV quantization of this Poisson sigma model, which describes open two-dimensional strings propagating on this Poisson manifold, that the perturbative three-point function of that Poisson sigma model, so the three-point function is this thing. It eats an open string, another open string, and an open string comes out. Remember the picture we had there? They show that this is the product, the deformed product of Kontsevic's formal deformation quantization. So we're not in formal deformation quantization here, but in geometric kind of non-perturbative quantization. So instead of the perturbative sigma model, I put the non-perturbative one so that you can reintegrate this, as we've described in this article here. And then its model stack of fields turns out to what is called in the literature the symplectic groupoid. It was proposed by Weinstein And I guess in the room there's people who worked on this. You can take the symplectic group out of X. Ping Shu, right? Yeah, he's not paying it. So it turns out this is an observation kind of hidden in the work of Eli Hawkins, who actually quantized the symplectic group, but after many years people just pre-quantized it. There are more people there. You have to raise your hand if I missed this. So what turns out, this carries a canonical circle, a prequantum bundle B to the 1 con, as it should for two-dimensional theory. So this is our X by S, or bulk theory, which I'm done in just 1 second. Now you check if the inclusion of the canonical inclusion of the Poisson manifold into this guy is formally a boundary condition, in the sense that Domenico explained in his talk, that I kind of kept alluding to, in the sense that here you have this transformation. So you can quantize this boundary correspondence. In the case where X is symplectic, it turns out the symplectic group point actually is Morita equivalent to the point. So what you end up quantizing this in K theory is this quantizes from the K theory of the point, or maybe the KK theory, you go, if this is the prequantum bundle, you have psi now, take psi, have K of X, and then you do the Umkehr map, the twist, the push forward here, using an orientation. So if this is now symplectic, sorry, I'm running ahead of myself here maybe. You can choose a Galler polarization, it reduces the spin structure, you can compute the index of the corresponding Dirac operator, and then K of the point. And this turns out to be, by an old result of Bott and some other people, you get a complex vector space, okay, over the point, which is the index of the prequantum line bundle under KK theory. This turns out to be the correct quantum space of states. So this is the correct quantization. Yeah, period. And from there we proceed. Thanks.